All right, welcome to our next video. Previously, we looked at how general networks can be analyzed and essentially converted over into a linear system and hence solved using our techniques. This video will focus on a more specific type of network, and as you can see by the name, it's an electrical network. So these are the networks that power everything around us essentially, right? Now, we're not going to solve or analyze the very complicated ones. We're just going to focus on the very basic ones, just to give you, again, another area, just a little bit more variety in how these linear systems can be applied. And the goal is to be able to take a network of a certain form, convert it to a linear system. So I won't be actually solving the systems. We'll just be focused on the setup. I think at this point, we're all getting very comfortable and hopefully very proficient at solving this system. So let's focus on the setup as opposed to the elimination. Now, I'm just going to make a few quick notes about some of the basic ideas of the networks or circuits that we're going to analyze. So I'll start with just some basics of electricity, right? I'm just going to focus on the aspects of electricity that will apply to our networks or circuits. So first, I'll just make these as bullet points. So current for us, well, not for us, but for a lot of people, measured in amperes, and we abbreviate that with an A. Resistance, right? So resistance is measured in ohms, right? So, and that's after an actual person, right? So in ohms, and that's the Greek letter omega, right? Uppercase omega. And it turns out that the product of current, so if I take my current and I multiply it by my resistance, I'll get the voltage, right? So the product of current and resistance is voltage, and that's abbreviated V, right? So now as far as the the abbreviation is V. Now as far as the notation that we will use, we're gonna use I, uppercase I, to represent current. We're going to use uppercase R for resistance, and again over here we have our voltage is V, right? Now, in any electrical network slash circuit, you're going to have several components. You could have a lot of components, right? Well, we are just going to focus on two types of components. Our circuits will have battery. So let's list the components. So our components will be batteries, and like when you look at the drawing of an actual circuit, we're going to use this symbol to represent a battery. So it's like that, and then like that. And the longer side here represents the positive terminal. So sometimes you might actually see that. And then the shorter is the negative. And in general, conventional current flows from positive to negative, right? So, let me use like a red to indicate the flow of the current, right? So, and that red just indicates the flow of the conventional current, right? There are other things flowing in a circuit, so for instance, electrons flow in a circuit. Well, they tend to flow in the opposite way, but we're just focusing on conventional current. What else we're gonna have? Well, we're gonna have resistors, and they do what their name says. They resist the flow of current. And so our symbol for resistance is like this kind of jaggedy edge type thing, right? So, and that's it. So these are the components that will be in our circuit. A battery, right? It's going to give us some, uh, uh, and our resistors. And our goal is to figure out what's the current that's flowing across each of the resistors in this, right? So our goal is to find I, right? So our goal, or all the I's. So the goal, find I's, right? Well, in order to do that, we need some guiding principles, right? Well, actually, before we get to the guiding principles, I do have another basic definition as far as circuits are concerned. So we need the notion of a junction. So a junction or node, like we used earlier when we were talking about our general networks, is a point where at least three paths meet, right? So where at least three paths meet, right? And these paths are similar to those connections that we saw in the general network. So where at least three of them meet, we're going to call that a junction, right? So good old Kirchhoff. And again, it's really strange though, when I do any research about Kirchhoff, I see so many different spellings of his name. So this is the one I'm going to use today. So here is the guiding. There are two guiding principles that we need. So here are the principles that's going to allow us to take all this information and put it into equations, right? So the first one, it's basically saying that all current, so all current flowing into a junction must flow out, right? So must flow out. And that's what we had previously in our general network. That was what I described as that conservation property, right? But in this case, it's related to current. So it's the inflow, or the sum of the inflow is equal to the sum of the outflow, right? The other one now has to do with the with the current and the resistance. So, and this is where we're going to use our property up here. Let me go back up. That says the product of current and resistance is voltage. So we're going to use this one to define our second principle that allows us to create our equation. So what it says is this: the sum of the product of I, so the current, so all the currents, all the resistance is that even a word? Yes. So the sum of this product around a closed path, and I'll show you what that means in a second. So around a closed path is equal to the total voltage in the path, right? So is equal to the total voltage in a path, or in the path. Let me just get this off. Here we go. So we have a closed path. The sum of the products of IR must be equal to the total voltage in the path. And that's all we really need because it's a relatively simple circuit when we just have batteries and resistors, right? And these two will allow us to create our equations. So let's start by setting up a really a simple one, right? And so the goal is to get through two examples here where we can analyze the circuits and then construct the equations. Right, so I'll draw this one. All right, so let's maybe start here. We have a resistor, and then we have our battery there. And we're gonna, this will be a junction, so I'll go ahead and put a circle there like we did earlier in our previous general networks, and then we're gonna have another resistor there, and then we're gonna come to another junction here, and then this one goes there. And then now for me to call this a junction, remember we have to have at least three if we go back up, we have to have at least three paths there. So I have two, so I have to essentially connect another path here before I can call it a junction, and that's what we're gonna do. We're gonna go here and down. Oh my, let's do this. Right, so there's our resistor, and then let's put another battery here. And there is the positive terminal, negative, and then let's close that path there. And then let's put some values on. So this resistor, let's say it has a resistance of 3 ohms. This resistor, 2 ohms. And then this one, 4 ohms. And let's say this is an 8-volt battery, and this is a 7-volt battery. And what we don't know is, we don't know the current here across this resistor. So let's call that I1. We don't know the current across the resistor in the middle. Let's call that I2. And then we don't know the current right here, I3. All right? Okay, so let's go ahead and do the analysis and then convert this into a linear system to see what we would have to solve in order to figure out I1, I2, I3. Right. So let's first do, what I often call the nodal analysis. So that's where we're going to look at all the junctions or nodes and write down, apply that principle that says the sum of the inflow has to be equal to the sum of the outflow. Now in this case, it's only we only have 2 nodes, right? So I'm gonna let's go ahead and label them as we did in the general case. So let's call this 1, let's call this 2. So at node 1, what's flowing in, what's flowing out? Well, we don't really see, there are no arrows here. Now, sometimes arrows are drawn, but what helps is that idea that your current is going to flow from the positive terminal to the negative. So it would have to flow basically along here, right? So it would have to flow around here, and then across here, and then back to here, right? So even if the arrows aren't on there, we can label it that way. And then similarly for this one, it's going to flow again from the positive to the negative. So it's going to start here, it's going to go around that way. Again, something's going to happen at that junction, right? And then it's going to come back around here. Sometimes you might even see on certain diagrams they might draw a little a loop type thing, almost like this, saying, "Yep, that's the flow around this loop." And we'll talk about loops in a second. And then loops or closed paths, and then like that, right? Okay, so let's see what's going. Now that we have a sense of the direction of the flow, let's write down the equation. So at node 1, we have I1 flowing in and I3 flowing in. So we end up with I1 plus I3. That's the inflow. And then look at what comes out of it, right? I2, right? So we end up having I2 there, right? So that's at node 1. Well, if we apply the same principle at node 2, are we going to get anything different? It doesn't look like it. Let's see. What's flowing into node 2 is I2. And then, right, nothing else. And then we have what's flowing out of it is, we have our I3 going this way, and then I1 going this way. So if you notice, what we end up with is the exact same equation, right? And that's not a surprise, right? So essentially, when we analyze the nodes in this particular electrical circuit, we get the same equation. So we basically have one constraint at this point, and if we want to find a unique values for all of these currents, which should be constant, right? We're going to need two more constraints, and that's where the other principle comes in about what happens in a closed path, which we can also refer to as a loop, right? So let me just scroll a little bit to the right here, and then now let's do what we're going to call a loop analysis, right? And the other principle of Kirchhoff, he says, this is what he says: the sum of the product of the current and the resistance must be equal to the voltage in a closed path or loop, right? So when I refer to when I use the word loop in this context, I'm using it essentially as a synonym for closed path, right? So let's start. So let's say this is, I guess we could label it if we wanted to label it. So let's say this is loop 1 that goes essentially the left half of the circuit here, and then this would be loop 2. So if we did, let's look at what happens around 1. Okay, so in this loop, we have two resistors, right? So if we take, so remember what it says, it's the product of the resistance and the current. So here I would have 3I1. So let me do that. So 3I1. And then I have to add that to the other product of, again, resistance times current. So that would be plus 2I2. There are no other resistors in that loop, but what we do have is our battery, and the principle is that this sum has to be equal to your voltage, right? So your total voltage, which in this case is 7, right? So there is a second constraint now that our currents have to satisfy. And then finally, let's look at what happens in the closed loop, which is what is the right side of our circuit right here. Same principle. Product of resistance times current has to be equal to your total voltage. So let's say I start with the I2. So I'll have 2I2 and then plus 4I3. That has to be equal to my voltage of 8 volts. Right? And there we go. There are the three equations that we need, right? So if I don't need to write all four because two of them are identical, right? So you could say that one of these is redundant. So let's write, if we were to write this system in standard form, starting with this equation, and again, this is the sum of the inflow equals the sum of the outflow. I can write this as, if I subtract the I2 from both sides, I'll have I1 minus I2 plus I3 is equal to 0, right? And in your system, you're going to have at least one of these equations based on the nodal analysis. You're going to have at least one of these equations where you have this combination of currents, right, being equal to 0, right? Again, that's that version of that conservation law. And then let's do our write down our loop analysis equation. So we'll start with the one that I have labeled here. So 3I1 plus 2I2, no I3 in that loop, that's equal to 7. And then finally, the third equation now, the second of our loop equations, 2I2 plus 4I3 is equal to 8. And now, I love doing this because what it does, it takes this very physical thing. These basic networks are like the building blocks for all our devices. So 3, 2, 0, 7, and then 0, 2, 4, 8. So we started out with this, our circuit. Again, very real. People build these in labs every day, and then we were able to create this mathematical abstraction of that object, right? Just beautiful. All right. So again, as I said, I'm not going to solve. If you want to go ahead and solve and earn a nice reward, let me know. We can, work out a deal, have your people call my people, that type of thing. All right. So there we go. So that's our first example. I want to do another one where it's a little bit more involved, right? It's a little bit more involved. But let's see if we can apply our principle and set up the system. So let me go down here. So this is our second example. And so what I will do first is I will draw the junctions, right? So this electrical network will have 4 junctions. And then we're going to have a resistor there. And we're going to have a battery there. And another resistor there. And then down back here. And then we have another resistor here. Maybe I'm drawing it too small, but we'll make it work. And then there we have another resistor here. and then there to another junction, and then we have another resistor along that path. Oh, and I forgot there is a battery on this side too. So we have a battery here, and then there, and then here is our resistor, a little small resistor, and then we have one more closed path. So down here, here is our resistor, another battery right here, and then we close it. There we go. Okay, so this particular circuit has 6 resistors and 3 batteries, and we're gonna set it up and solve. So let's label what we can label. So I'll start at the top and I'll put I1 there, and then this resistor, so the resistance here is 4. Excuse me. The voltage here is 14, right? This resistance, so 6. So I'm not writing the units, just putting the values there. This one, and then the current here, the unknown current is I2 for this one. The unknown current here is, let's see, I think I had this as I3, and this is I5. The resistance across this resistor is 2. This one is 4. This one is 3. The voltage here is 18. Voltage here is 16. Resistance is 6. And then I had this labeled as I4, right? So I think we have everything labeled. And again, based on what we see, we can write down the flow of the current. So again, the longer edge there is the positive side, and the conventional current will flow from the positive to the negative. So it'll go that way. Same thing here. So this one, positive to negative, so it's going to go back this way and around. And then there is one loop, and then finally positive to negative, so it's gonna go this way, so like this, and then up here, right? So you can see it looks like there is let's see, actually, and okay. So now let's see if we can set this up. So let's do our nodal analysis. Right? And if we label them, so we have 1, like I said, this network has 4, 1, 2, 3, 4. So at 1, we have I1 going in and I2 going out and I5 going in. So we have I1 plus I5 is equal to I2. Right? If we look at node 2, which I have labeled here on the right, we'll have I2 going in, and then I1 and I3. Actually, I didn't label this one, so this will be, this here is I6. Yep. So what we have going in is I2, and then we have I1 and I6 going out. So I1 plus I6. And so far we're getting different equations. So at node 3, we have I5 going out, I and actually no. I have something. Let me fix this. Let me fix this. And then that arrow will be this way, right? So at 3, we'll have I3 going in, right? So across, yep, so right here, so I3 going in, and then going out, we have I5 and I4 down below. So I5 plus I4. And then finally at node 4, what do we have coming out of it? We have I3 coming out, and we have I4 going in from here this way, and then we have I6 from here going in, right? So there should be a little arrow here. I really should have drawn this bigger. But at node 4, we end up with I4 going in, I6 going in, and then I3 going out. All right, so that's the node. So now we have to do the loops, and there are 3 loops or closed paths. So we're going to do our loop analysis, right? And we'll start from the top and work our way down. So in the top, we'll have 2 products. We'll have 4i1 plus 6i2. That's equal to 14. Right? So again, the sum of the products of our resistance and the unknown currents, that's equal to your total voltage. So right there. Now let's look in the middle. For the middle loop that goes this way, we end up having 4 products. So let's start with the smallest subscript. So 6i2, and then the next one will be 4i3, and then I5 would be 2i5, and then we'll have 3i6, and that has to be equal to, well, there's only one battery in that loop, and it has a voltage of 18, so equals 18, right? So there's one equation, there's our second, and then now our third. So for the bottom loop, we'll have 2 products again. 4i3, that's this one, so 4i3, and then plus 6i4, and then that will be equal to the voltage of 16. Right? And there we have, how many equations? We got 7 equations, and now if we look at this, right, so we got our 7 equations, and we can put this in augmented form if we would like, right? So let's start with these, and I'll write these in standard form. So I have I1 minus I2 plus I5, that's equal to 0. And then here I'll move I2 over, so I'll have I1 minus I2 plus I6 is equal to 0. Third equation there tells me I3 minus I4 minus I5 5, that's equal to 0. And then our last nodal equation is if I move over the I3, it becomes negative I3, and then plus I4, and then plus I6. That's equal to 0. And then our loop equations, so the first one is 4I1, and then plus 6I2, that's equal to 14. And then the second one, so 6I2 plus 4I3 plus 2I5 plus 5I6, that's equal to 18. And actually, no, that's not a 5. This is a 3. It's a 3I6. So plus, and then I think, what did I erase right here? This is the third one, so this should be I5. There we go. And then our last equation is 4I3, and then plus 6I4, that's equal to 16. So now let's see if we can write down the augmented matrix for this. Okay, so 1, negative 1, then I have 0, 0, 1, 0, and then on this side I'll also have a 0. And then I have 1, negative 1, 0, 0, 0, 1, and then 0. And then I'll have 0, 0, 1, negative 1, negative 1, 0, 0. And then the final of the junction or node analysis. So we'll have 0, 0, negative 1, 1, 0, 1, 0. I'll probably have to make this a little longer. And that's why I didn't even close that side, but this should be sufficient for the remaining 3 equations. So we have 4I1, 6I2, and then nothing else there. That's 14, and then 0, and then 6, and then 4, and then 0, 2, 3, and 18, and then finally 0, 0, 4, 6, 0, 0, and then 16. And that is the augmented system that represents the solution to this particular network, right? So you just have to be careful in terms of, again, identifying the junctions, identifying the loops, and then applying one of the 2 principles for Kirchhoff to convert that circuit into a set of equations, right? And this would be a fun task, going ahead and eliminating this, right? So again, let me know if you're up for some fun. See you in the next video.